Hello, I'm Yaroslav and I'm in charge of customer support at Lightnovo.
Alexei, CEO of Lightnovo, and today I would serve as operator for Yaroslav and for our new device. Yaroslav, tell us about it.
We would like to present Lightnovo RG Pro Raman Spectrometer. Lightnovo RG Pro allows to access low frequency Raman range as low as 25 inverse centimeters. This specific device I'm holding in my hands has an excitation wavelength of 785 nanometers.
Yeah, I see it also comes with accessories when you order it, yes?
Yeah, various accessories. We have different probes. Here we have a middle distance probe mounted on a device. We also have a long distance probe. We have a contact probe. We have a polystyrene reference sample for testing the calibration. We have a USB stick with the software and calibration reports, and so on.
Yes, we are very proud of this device, but before speaking how good it is, let's demonstrate first.
Yeah, so over here I have a bunch of samples, and let's start with sulfur. Sulfur is a reference sample for low frequency Raman shifts according to ASTM standard, and let's measure it. So I take sulfur,
I said I will serve as operator, so let me also capture. Yes.
And we have a bunch of lines at low frequency Raman shifts. And let's go to the very beginning of the spectral range. And we see these lines. So the first one is at 25.9 inverse centimeters.
Yes.
And the line at 50 inverse centimeters. As we see, the calibration of the device is pretty good. We also have some other lines at longer Raman shifts, up to 500 wave numbers. So.
Yes, very nice. So sulfur actually used as a sample to check the very low frequencies, and we just did that. Let's measure something else.
Yeah, let's measure paracetamol, and it's also another sample for Raman shifts calibration. And in this case, we can measure it right through the plastic packaging.
Okay.
And
let me help you as usual. Signal is good, you think?
yeah, it's pretty good.
Okay. So
and over here, what we see the fingerprint region over here, and it's like typical fingerprint spectrum
this
of the
one.
material, for the characteristic of paracetamol. And we have the low frequency range, and low frequency range tells us about intermolecular interactions about the samples and basically polymorphs of the material, how it is crystallized, and it is extremely important for pharmaceutical industry.
I can see it's around 32, this peak.
Yeah.
Okay.
And depending on polymorph, the shape of the spectrum in low frequency region would be different.
Something else?
Sample I have is a tablet of ibuprofen. And actually, when we were measuring this tablet, we found out that there is a coating of titanium dioxide, and inside we have ibuprofen. And if I measure outside, I measure the coating. Let me focus it better. Let me focus it. Over here, we see a typical spectrum of titanium dioxide.
Yeah.
So 3 peaks in the region of around 500, and 1 peak at around 180, I believe.
Yes, and I have a feeling that these two little peaks, they probably already from low frequency modes of ibuprofen.
Yeah, could be that the coating is relatively thin, and then we shine the laser through the coating and we pick up the strong low frequency modes.
So now we measure inside the tablet.
Inside the tablet.
And how it looks.
And
maximize the signal a bit, please.
yeah.
Okay, let's try like that. Let's show that there is a fingerprint range.
Yes.
Yes, definitely it is, and low frequency Raman as well. So I think my guess was right. Through the coating we also saw the low frequency peaks of ibuprofen. Very nice.
Actually, I also have another sample. It's a reference sample. It's Calcite. It's to test the resolution. And actually, an advantage of our device is that we capture all the spectrum starting from 25 inverse centimeters or so up to 2000 and something, so basically covering low frequency range, fingerprint region, and
2000 and
part of
something. 2000, how much?
200
exactly?
I think, and part of silent
Yeah.
region, so it
Yeah,
goes
yeah.
all the way to silent region. And let's measure the calcite, and we
calcite
have
peak.
this 1085 inverse centimeter peak, which is the standard for testing the resolution, and then we can check the resolution from the full width half maximum of this peak, which is around 4.5, let's say, wave numbers.
Yeah, you see one net here is 5 and we are slightly less than that, also
And
understanding.
then there is the formula to convert, so
Yeah,
we can
natural
estimate like
broadening
4,
of calcite.
4.5.
But the actual resolution would go from 3 to 5 inverse centimeters through entire spectral range, which I think it's a very great performance for such a broad range. It's really hard to reach less resolution if you want to cover entire spectral range.
And then it's enough for recognition, for identification of materials based on their spectrum, and as well as for the analysis of low frequency spectral range. So as we have shown, low frequency spectral range finds its application in pharmaceutical industry. In addition to pharmaceutical industry, it is extremely important for polymer industry, where we also look at intermolecular interactions and structure of the material, which is important for optimizing the processes in polymer industry. As well, it finds its applications in semiconductor industry, where with low frequency we can look at Feynman modes of different materials. For example, quantum dots, 2D materials such as graphene, molybdenum disulfide, and so on.
Yes, definitely. And to finalize the discussion, Yaroslav, please help me. In terms of design of this unit, inside we have interference filters instead of typically used Bragg grating type of filters, and those are very expensive. And we, trying to follow Lightnovo vision, we have specially developed interference filters that allow us to go that close. And interference filters are way less expensive than Bragg gratings. That's why device is still affordable, allowing us to reach low frequency Raman range. Another benefit of interference filters, they are larger aperture allowed to be used, and which means higher throughput. And another reason, they are way less critical to the different angles of stray light getting through, which means way less stray light on a sensor. You can allow longer exposure times, and you still see only the peaks and spectral signatures of your actual sample, not the artifacts of the device driven by the stray light. So there are numerous benefits. Please try it, enjoy, and thank you for your attention.
Thank you for your attention.